Hello, welcome to this video about math classics. Today I'm going to talk about topology. After these four exercises, I found one that I find really interesting for understanding topology. So, if E is a metric space, do E and the closure of E always have the same interiors? We will call D the statement, may E be a metric space, E and closure of E have always the same interiors. So let's see that. It's a topology question. So where is this? Okay, so we have our statement D. The interior of space A of a bigger space X, so A is a part of X, is the biggest open set of X included in A. So here are two notation with the operator int or with the little symbol here over the letter of the space. So that's the definition of interior. For the closure, so the closure of A is the smallest open set that contains this part. In French, it's called adhérence. It's called adhérence. So I have the habit to use that word instead. So if A is a metric space, the closure of A is also the set of all converging sequences inside A, because the topology will stay inside A. So these definitions are equivalent if A is a metric space. So this is the international notation, and this is the French notation, but I have the habit of using this one. At first, to start the exercise, I'm going to talk about this formula. So the interior of E is always inside the interior of the adherence of the closure, of E, because the adherence represents the limit. So imagine you have a sphere, so the interior of the limit is bigger than the interior of all the sphere, because the adherence is slightly bigger than the space. And actually we can write the adherence as being the union of the metric space E and E prime, where E prime is a set of limit points of E. So that's it. So we have two possibilities. Either the interior of E is always equal to the interior of the closure of E for every metric space, because that will mean that even though that would mean that, imagine you have a sphere and the limit of the sphere is so that the interior of that limit of the sphere, the exterior of the shape, is the same as the interior of the sphere itself. Actually, it's not a sphere; it's a ball, but it doesn't really matter. It helps to represent how it looks like. So that would mean that the limit is the same as the original space. So as we've seen in that definition, so E prime wouldn't have would have the same interior as E. But so that's the first possibility, and then that would imply that D is true, or there exists a metric space so that there exists an element of the interior of the closure of E that is not in the interior of E. and then D would be false. So it would mean that the limit points is slightly bigger than the ball, the ball of the space. So imagine you have a sphere, and the adherence of that is bigger than the 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 ball, but the problem is that the it must be an open, yeah, the closure of A is an open set, so that would mean that you have an open that is the closure, that is the closure, the adherence of that ball. So that would exist, that can exist, and then that would imply that D is false. So we have two possibilities. So you have two options. The first is to try to demonstrate that D is true for all metric spaces, and then the question will be really hard, because proving that is very, very hard. Um, so yeah, and the second option is that you can find a counter example, and then the question can be either yeah, be either easy or hard depending on the question, because you have to find an example that you can think of. So it's not like it depends if you get the correct idea at the correct time. So I know that D is false, so I'll find a counter example because I took the question. So I propose a solution to prove that D is false, so it's a counter example. So I know that the adherence of Q is the space of real, because Q is the space of fractions. I know that the interior of the fractions is the empty set, and I know that the interior of the space of reals is the space of reals itself. So the interior of the adherence of Q is R, because like C, we have this relation here, so it's using this one and this one that gives this fourth one. And so we have an interior of Q that is R, that is not the empty set that is the interior of the adherence of Q. So yeah, I think that's it, because we've proven it. If you have any question, feel free to ask them in the comments. I'll be glad to answer them. And thanks for watching, and bye.